Hi, and welcome once again to this channel. And before starting anything, I would like to say a disclaimer that this may not be the absolute shortest way to find the area of an ellipse, but this surely is one of the interesting and one of the unique ways of finding the area for sure. This certainly will improve your understanding and will try to build a connection between a circle and ellipse and why their areas are so similar, and not just why they are so similar, because like ellipse is a more general case of a circle, rather than to really find out as to why they are equal, I mean similar. So there will be some prerequisites to this uh, video. Once you know previously that what is an ellipse and what is a conic section, for that matter, and since you clicked on this video, I would hope that I would I mean it's obvious that you know what is an ellipse, like the blue circle, the blue not the blue curve inside the red circle is the ellipse. That's how the ellipse looks. But there are also other prerequisites, like you should know what is the general and the standard equation of a ellipse looks like. That may not be that much of an important, but it is surely required. And you should also know what the definition of an auxiliary circle is, which is the red circle that encompasses the ellipse in this case. And you should also be familiar with representing points in 2D curve in 2D planes, and planes are 2D. So in planes, that the points are represented can be represented by the distance of the point from the origin and the angle of elevation. uh, the angle of elevation is again translated to sine theta and cos theta in this case. Now let's start with finding the points, like the general points on this of on the periphery of this ellipse and the auxiliary circle. Yeah, so auxiliary circle means a circle that helps to do stops with the ellipse. So each ellipse has its own auxiliary circle. Start with finding the points, the general representation of points on the ellipse and the circle for that matter. Like for the specific case of the ellipse that I have drawn, its x coordinate can at max vary till plus 5. I mean, it ranges from minus 5 to plus 5, and so does the x-axis, x coordinate for the circle, right? So we can safely assume that the x coordinate is a cos theta. Here theta is the variable, and as you change theta, x can vary from minus a to a, and for this case a is 5. So I'll write down that here. For our case, uh, the points can be represented as 5 cos theta, and if you put this in the general equation, not the general or the standard equation of the ellipse, I mean they are like they can be interconverted very easily by shifting the uh, origin, but still I won't be using the formal wording. I will be saying that when we put this in the simple, in quotation mark, equation of the ellipse, which is for this case x square by 25 uh, plus y square by 9 is equal to, is it 9? Yes, it's 9 is equal to 1. When you put this value of x in this equation, y turns out to be, you can check, 5 sine theta. Now this is all that is for the ellipse. Now if you put the same coordinate for x, which is possible, right? Like both of them can have same coordinate of x, but I'm not saying that they will have same coordinate for y, which is like absurd. They won't. Like you clearly see red patch in which their y coordinates are not the same. I mean, also in the red patch specifically for this portion, All the y's that are in this portion will never be found in the equation of the uh, ellipse. So when you put that a particular value of x in the uh, equation of the circle, you get uh, 5 cos theta comma 5 sin theta. So this is the general and the most simple uh, uh, coordinate of a point on the ellipse. This one is for ellipse. I can mark them out, ellipse, and this one is for circle. Now let's start with the formal derivation part. I'm erasing this. I will start by drawing a particular line segment from a particular a random point on the periphery of the circle, auxiliary circle, and onto the uh, major axis of the ellipse. Um, so, as you can see, the 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 perpendicular to the major axis segment that I have drawn is certainly cut at this point. Um, we can actually find the distance of the length of this segment and length of this segment. Let me name this segment as A and this segment as B. So, what is B? Like, I can assume this has to be maybe some point according to this equation, um, maybe 5 cos phi. Let's not use theta just to be fancy. So this point would be 5 cos theta, and y would be specifically 3 cos phi. I'm writing phi below, excuse me, because the general um, coordinate of the point is 5 cos theta and 3 sin theta. So we directly got that the b is 3 cos phi, right? And now if you try to find the value of a, you can just notice that the coordinate of this point will be something like 5 cos phi comma 5 sin phi, right? So as a whole, this distance is 5 sine phi, and this distance is, as I've written, I've not written, sorry, 3 sine phi. So what we can do is, to find the value of a, we can just subtract those and take the modulus. So we will get the value of a as 2 sine phi. Once we have done that, we can actually find the value and keep that in mind of a by a plus b, which is in this particular case 2 by maybe 5. And let's also keep the value of b by a plus b, which is in this case 5 3 by 5. This will be of prime importance later, but I have just done a blunder because I have assumed ab to be something in this case and other in this case. So let us just say that this is not b, this is l, this is m. So this, let's cut this. This will be something like I don't know, maybe uh, L by m plus L. And if you notice here, L is nothing but okay, let's not think about that now. We only got this much. So what we essentially got is this value is constant for any point on this complex x and y coordinate. Not complex, but two curves there. So I'm saying that's complex, but it's not complex. Trust me. I'm just erasing them. Sorry for the wait. Okay, never mind. And if this value is constant for every point, I mean every line segment that I such described, then what we can say is, like, now let us construct not a line segment but a line segment with a little bit of thickness. So it's not, it's basically a rod kind of thing, but really approximated to a line segment when we assume that the distance, like I mean the width of the rod to approach zero. So let us construct that like this, and the length is like nearly zero, but not absolutely zero, because we need to like stack them one beside other to uh, form this whole area. We need to form that actually. So in this rod kind of thing, in this histogram, I mean not histogram, bar kind of thing, um, the red portion to the blue portion is the value of m by l, and what we're interested is in l by m plus l. So this blue portion to the whole of the rod, that will be also equal to 3 by 5, almost also equal to, not even almost, because every single line on that, on this rod kind of follows this proportion. So the rod as a whole will follow that proportion. And when you extend this rod, you not extend this rod, like keep another rod of a shorter length uh, right here, and then uh, again shorter here. And if you go doing like that, what you end up is, where you end up is tracing the whole curve and the whole upper hemisphere of this, not hemisphere, like upper semicircle of this a whole figure. So in short, what you have just found out is, like, the area of this region to the area of this whole semicircle is 3 by 5. And essentially 3 by 5 has just popped out because of 3 divided by 3 plus 2, which in essential, I mean, which is essentially a by a plus b, right? Oh, sorry, again I did the same mistake. It is not a by a plus b, it is like l by m plus l, and m plus l is 3 plus 2, and which is l plus m is actually, if you remember the initial rod that we made, l plus m was like, l was this much, if I'm not wrong, yes, and m was this much, right? So l plus m is the total length of the rod, which was if I'm not wrong, 5 sine phi, yeah, some of this too. So it was like 5 sine phi. Here 5 is the value of l plus m, and which is also the value of a, right? So l by m plus l is nothing but b by a, basically. Now if you essentially extend this uh, extrapolation, I mean extrapolate this this description to the whole circle, what you will end up getting is the area of this ellipse to the area of this circle is nothing but b by a. And this can be procured if you get the area of the ellipse and then you get the area of the circle. But what we did is just proportion, right? Not proportion, but ratio, and extrapolating that ratio to areas, and then combining those areas to encompass whole of the figure. That is all that we did, right? And then ended up getting this ratio. So basically, you now know the area of the circle, right? Which is, yeah, sorry, this pi a square. For this particular case, a is equal to 5, as I have written here. What that means is the area of the ellipse is nothing but pi a square into b by a, which is pi b. And the only area kind of thing that we actually used in this derivation is the area of a circle, which is, I think, known to everyone. But uh, actually finding out the uh, area of the ellipse, which requires calculus if you do x wise or you do y wise, is not actually known to everyone, right? Like, there have been various analogies made where you open up the circle and form a triangle, and then you find the area of the triangle to get the area of the circle. But I honestly think that this was something new. I don't think, I mean, I have not seen this process of finding the area by ratio. I think it's new. I hope you liked it.